Oh. Resume the recording so that anybody can refer back to this lecture later. Welcome everybody. Let me just make sure that I'm letting people in as they come up to the door. And at the bottom of the screen, you have a reactions button. So what you can do if you want to say that, yes, I can hear you, give a reaction, thumbs up, like this. That's a reaction to say thumbs up. And let me admit, Kieran is now entering the room. Exactly like a real lecture that some people are going to be early and some people are going to be a little bit late. So as they come, I'll connect them in as we go. And okay, just keeping an eye on the people here. So, welcome everybody to our first Year 4 online lecture. And last week we did sound. This week we're going to look in a little bit more detail on ventilation. So I hope that you've got your pen and paper ready with a separate calculator to your calculator for your, if you're looking at this on a phone. What I can do is just temporarily, let me just make sure everybody's on. Okay, right. I can unmute all of you and now you should be able to say hello if you want to say hello before we start. Hi everybody. Right, let's get started. So what we're going to do this morning is look at ventilation in more detail. So in Zoom, you have got the option, I'm going to share my presentation with you, and then we're going to take it really slowly and discuss it nice and carefully as we go. It's easy maths, but we need to take our time to go through it. I'm going to send a chat message now. Can everyone see and hear me? If you just get used to, so that chat message, if you reply to that chat message just to say yes, 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 you should be able to say Yes, yes, yes. Yes, lots of yeses. Excellent. So what we're going to look at, I'm going to switch now to the, ignore my tweets, I'm going to switch now to the PowerPoint presentation, and I'm going to share that screen, and we're going to go through it really nice and slowly. So I'm going to switch over to PowerPoint. I'm going to start the presentation. Then I'm going to go over to share screen, and what you should now see on your screen is a PowerPoint slideshow. So here we go. So we've already gone through the importance of airtightness, and I introduced a few weeks ago the principles of mechanical heat, ventilation, and heat recovery. We're now going to look in more detail and behind the mathematics. Let me enter, hold on, admit Ina. Hi Ina, welcome to the group. I'm sorry that you haven't missed anything yet. So I'm just going to mute you for the time being. So everybody should now be muted. So yeah, it's the detail and the mathematics behind the air that's required in order to not suffocate in the building. So let me admit Tiffany. There we go. So obviously when we have an airtight building, we need air to go into that building. So if we haven't got that air, what you'll find is mold growth in hot rooms such as bathrooms and kitchens, black mold growth because there's too much heat in there and there's not enough ventilation. And obviously the room will get stuffy. And if it's so airtight, then obviously suffocate. So let's now go through. This was an image that I did a few weeks ago now on the principles of heat recovery and ventilation. That what you have is a heat recovery unit. This is shown in the roof here at the moment. And what effectively it's doing, it's bringing in lovely, clean, fresh air. And it's then going through a unit where the, sorry, I'm also getting stuff from, let me turn off Teams for the time being, sorry. Okay, sorry. It's also, so it's extracting the hot air from the hot rooms, such as the bathroom and the kitchen. And what it's doing then, it's pulling out that hot air. It's purifying it with the lovely clean air. It's taking the heat out of it, and it's putting the heat back into the rooms, such as the bedroom and living room, in order to give clean, pure, warm air into those rooms. All of the slides I'm going to show you today, I'm going to put onto my website, and we may also be starting to set up Moodle as well. And we also may be starting to set up Teams. We'll be looking at that in the next week or so. That's the principle of a heat recovery unit. This is what's called a centralized heat recovery unit. I'm just going to make sure my chat is on as well. There we go. So next slide. That's a centralized unit where there's a central unit up in the attic and it's doing what I just said. You can also have a decentralized system where you have small units such as this in the rooms, and each unit is working individually to bring in the lovely clean air, extract the heat, and push the new warm air back into the room. And any of the hot rooms, like the bathrooms, it's also taking out the moisture out of that room and then bringing the heat back into it. So it's like a decentralized unit where you've got a small thing that goes in the wall. So the building regulations for ventilation are, like I showed you with sound last week, are really short and simple. That there's two, F1 and F2. And we're looking today at F1. So the means of ventilation, this is all you have to do. We need to provide an adequate and effective means of ventilation for people and buildings so that you limit the moisture content of the air so that it does not contribute to condensation and mold growth. We also need to limit the concentration of harmful pollutants in the air within the building. Two simple things, dead easy. But obviously what you can do is let me go back a slide. That's the basis of the regulations. We saw last week in sound, there's a technical guidance document on what you need to do. I'm going to stop the sharing of this slide. I'm going to open up now what the technical guidance document looks like. So just pause in there for a second. I'm going to switch to Adobe Reader and share this document. Share screen, that one. So you should now be seeing on your screen the actual technical guidance document for Part F of the building regulations. This is the Irish document. There is a similar UK document. I think it's also called Part F. The Part F in Ireland is much more stringent than the one in Ireland, in the UK. So we saw the building regulation. If I skip through, we're just going to skip through this. I'm going to put it up online so you can read it in more detail later. So there's the actual regulation. This technical guidance document is the prima facie evidence that if you do it to these regulations, another participant coming in, admit. Sorry. Okay, management. Okay. This prima facie evidence, if you do it to these regulations, the guidance that they give you, then you will have proved using this that you have complied with the building regulations. So we're going to skip through it. We're going to see that the actual regulation that I just showed you on PowerPoint is here. And this is the breakdown of it. And if you adhere to these regulations, it gives you lots of guidance on the names of what things are, like we saw there ventilation strategy, air infiltration, continuous operation. It's giving you different options for continuous mechanical extract. I'm going to show you what that is in a moment. It's giving you heights of rooms. This is where that minimum height comes from. It's the ventilation part F, that the height of the minimum of a habitable room is 2.4 meters. That's where that comes from, is part F of the regulations. There's also an area calculation if you're doing rooms in attics, or in the roof space. We're going to be looking at this in more detail as we go. How much ventilation is required, minimum boosting for kitchens and utility rooms. As I said, I'm going to skip through this, but we're going to be picking out some of these things in more detail. And it's got, so if you wanted to go to the sort of the main document, this is it, part F. I'm going to make sure that you have access to that online. Now, what we're going to do next, I'm going to introduce the different types of systems. And what's really neat is that part F gives you, let me scroll down. it gives you some examples. So we're going to work through some examples for how much air is required for a room. So let me quit out of part F. I'm going to stop sharing that again. And I'm going to share back the PowerPoint slides. That's where we were. And that's the regulation. These are the types of systems that you can have to meet part F of the building regulations. These slides were provided by S&P, the most effective advice for the something ventilation systems. So what you can have is a mechanical extract ventilation. What it's doing is what I showed you in that other diagram. There's a unit in the attic. It is continuously extracting air from the wet rooms, and it's humidity and manually checking the speed. So it's pulling out the air from these wet rooms. But what it's not doing, it's not taking the heat out and recovering the heat. It is only mechanically extracting the air and the hot air from wet rooms so you don't get condensation in the bathrooms and the kitchens, for example. We have a second option. It's called demand controlled ventilation. Very similar to the first one. It is continuously extracting air from the wet rooms, the bathrooms and the kitchens. It is self-balancing, constantly balancing itself, and it's controlling the humidity. So it's like it's on demand. It's basically balancing it out on demand in order to make sure that there isn't any mold growth and any condensation in the bathrooms. The third option is a mechanical ventilation with heat recovery. That's the one that I recommend we have on every job, in that what we have is a centralized unit. It's the same diagram that I showed you previously, that we have a unit in the attic. It's bringing in the cold air from outside. It's pulling out the hot air from the bathrooms. So the cold air in is the blue line. The warm air from the bathrooms is the red line. It's mixing the two together separately, and it's pushing warm, pure air into the rooms that need it, such as the bedrooms and the living rooms. And that's the heat recovery that's going on in order to make sure that the rooms are at the right temperature. This is the system that the Passive House Institute insists on. We're going to look at in a moment at PHPP to show you the difference between having a system that's MHVR and not having it. You'll see, I've been saying MHVR, this one is MVHR, there's MHR. So generally, you're going to have to work out the different people use different acronyms for the different systems. The fourth one is a decentralized system. That was the second slide that I showed you before, in that you have small units in each room. They are then continuously extracting moist air out of the building, and it's then bringing the cold air in and warming it and bringing it back into the bedrooms and the living rooms. The advantage with this is that it doesn't need a load of pipe work and duct work through the building. The mechanical ventilation system is ideal for a brand new house. You can plan the ductwork. The ductwork can go through spaces that you've created. And probably next week, we're going to start looking at that in more detail about the ductwork for this. And whereas on an existing house, trying to feed ducts through, it's very difficult. So the decentralized system, where all you have to do is make a hole in the wall and then connect it up with electricity, is a very easy system for an existing house. And the fifth system is a positive input ventilation system. And it's usually a fan in the attic, and it supplies air via a hallway or landing, and it pushes air into these rooms. And the water vapor then comes out through natural leakages in the property. It sounds a bit dodgy to me. The one I use all the time on new houses is number 3, the mechanical ventilation and heat recovery system. And on existing houses, we use number 4 all the time. So they're the 5 systems. I'm going to stop the share on this slide. And hey again, I'm going to now share another screen. I'm going to show you PHPP. I don't think we've actually seen PHPP live. So in a way, the online lectures, they're an interesting way of showing stuff, and I can switch between things, and it's a more, I don't know, I'm getting used to doing it now. So this is PHPP. It starts with a load of tabs. This system was developed in Stuttgart, Germany, by the University of Innsbruck, by the unbelievably clever and genius Wolfgang Feist. I've met him a couple of times. I was on a field trip with him in Munich, and he was walking through a boiler room, and there was a tap on the wall, and he just felt the tap, and he said, they forgot to put the insulation on the tap here. He was going around touching pieces to make sure that he knew where air and heat leakage points were. Anyway, so here we go. These are the instructions. We have a verification here. Does the house pass the passive house methodology and calculations? And this is just a sample one that I've set up here to show you. We've gone through this a million times. I showed you this in Vectorworks. You have a heat load, space heating. We have a heat load, and we have a heating demand. This one's slightly over, but it's compensated elsewhere. It's 16 as opposed to 15, but it's meeting the regulations based on other things. So these tabs, as we work across the bottom of the screen, the tabs are each things that we enter in Vectorworks, in PHPP. So the verification says whether it meets the building regulations. We went through and saw different locations. We did last week's on Vectorworks. We showed the house in Galway. This is in Belmullet. And it gives you a check whether there's any errors in your PHPP. Then skip variants. The climate is where the building is. In PHPP in Ireland, we've only got Dublin, Birr, Cork, and Belmullet. So we can change it if we want. We've done U values to death. This is the PHPP U value. I got you to do it by hand. This is how easy it is in PHPP. You can see the U value here of 0.164. And what I've got here is 220 millimeters of insulation. If I change that to 300 mil, it automatically updates the U value calculation here. So it's pulling out this data. You can see the build-up here of the build-up of the wall and the build-up of the roof. It calculates the areas. If you remember from the Vectorworks demo that I did, we have treated floor area. We can see that here is 270.94. It's also working out, if you remember back a few weeks ago, we also worked out the areas of wall to glass. This is now doing it automatically for you rather than you getting a calculator out. So for example, if I have on the south elevation a user determined value of 138, where am I now? 138 meters of wall, I can change that to 150 meters of wall, and it automatically updates the calculations. We can choose the ground, each component. These are the ventilation units we used for this building, and we can also choose Scroll across. We can also choose windows. Go over to windows. These are the types of windows that we can choose, and different types of shading, whether you've got trees and stuff. Anyway, the one I'm looking at today is ventilation. So if we go back to the verification, me changing actually a couple of things in it. I only changed the location of the wall. It's dropped now down to 10 kilowatt hours per meter squared per annum. So with this system, if we put in an MHVR system here, it drops to 10 here. If I change it to just an air extract unit, that's a unit that's extracting air only, it's gone up to 20. So immediately you can see that the MHVR makes a big, big difference on your heat balance and a low energy build. And if we only have window ventilation, just windows opening, if we go back to verification, it's increased again. So you can see how that affects why it's important to have MHVR. So let me stop that and switch back to, hey again, let me switch back to PowerPoint slideshow and share this. We are now going to very slowly work through an example where we're going to work out how much ventilation is required for a house that is 130 meters squared. It's semi-detached. It has 3 bedrooms, 1 bathroom, 1 utility, 1 sitting room, 1 kitchen, 1 dining room, 1 downstairs toilet, and 1 internal ensuite bathroom. Now, I showed you part F, so I'm going to pull out things from the part F to show you in this slideshow. So, what you need therefore is a pen and a paper and several sheets of paper and a calculator. So, we're going to go through this nice and slowly. We have lots of examples to do here. So if you were going to have just mechanical extract ventilations, that's pulling the air out and taking the warm air out of the hot rooms and bringing warm air into the cold rooms, making sure there's no condensation in the bathrooms. This is how it's worked out. This is called a CMEV system. Continuous mechanical extract ventilation. It is continuously and mechanically extracting the ventilation. One thing that I should have said, after I've stopped this slide share, we can switch up. There's a thing where you can put your hand up and stuff. I won't do it yet, but we'll see how we get on with it. So, what this house, the air that's required for this ventilation system is that you have 5 liters per second. So if you imagine a liter of milk and fill it with air, we have 5 of those for plus 4 liters per second per person. So that means if the managed participants, sorry, just managing participants there. If we have a 3-bedroomed house, the way that it's worked out is that you have 2 people in the 1st bedroom, 2 people in the 2nd bedroom, and 1 person in the 3rd bedroom. So that means there are 5 people in the house. So let's go on a slide. So what it needs to work out is that you have 5 liters per second, and then for every person, and we just calculated that it's 5, you have 4 liters each per person. So if you multiply 5 people by 4 liters per second, you get 20 liters per second, and then you add on the 5. 25 liters per second is the calculated general ventilation rate. Or, so that's one number that we've got. And I'm going to, once I've done the slide share, I'm going to show you the principle of what we're doing, scribbling it out on a piece of paper. Or, it is 0.3 liters per second per meter squared of the building. So, we have in this building 130 meters squared, and it's 0.3 liters per second per meter squared for that. So this is how you work out the second bit of the calculation. You have 130 meters squared, that's the size of our house, at 0.3 liters per second per meter squared. So you multiply 130 by 0.3, and it gives you 39 liters per second. Now, if you look on the left-hand screen, 1.2.2.2, it says, which is the greater of those two numbers? Is it 39 liters per second, or is it 25 liters per second? So the greater of those two numbers is obviously 39 liters per second. So the general ventilation rate of that house is the highest of those two numbers, which is 39 liters per second. Okay, that's stage one. What we're doing in this, let me turn that off for a second. Now, can everybody see me? You can, I think even with your video turned off, I think you can give a reaction. Can everybody see me, see the screen? You can either say yes in chat, or can everybody see what I'm doing? Thumbs up, thumbs up. In the bottom right, there's a thumbs up. Excellent. So everybody can see, hopefully see what I'm doing here. So so here's the sheet. I'm going to, every now and again, I'm going to scribble something. So this is what we can do when we scribble something. So we've got, we need to work out the, start again. We need to work out the general ventilation rate. That's what we're working out, the general ventilation rate. And we have two methods to do it. Method 1 and method 2. And method 1 is 5 liters per second plus 4 liters per second per person. Method 2 is where you have 0.3 times the area. And this goes on to whichever is the greater. Whichever is the greater of those two moves on to the next stage. And in this example, the answer was 39 liters per second per meter squared, I think it is. So I'm going to switch now back to the screen, share the screen again. Back to PowerPoint. So it's 39 liters per second there. That's stage 1. We're now moving on to stage 2 of this process, where we have to work out, because we've got wet rooms here, how much air needs to be pulled out of those wet rooms to stop there being condensation in those rooms. And this, from table 1 of the TGD part F, is the calculation and numbers to do that. So, recap on the house. We have 3 bedrooms, 1 bathroom, 1 utility, 1 sitting room, 1 kitchen, 1 dining room, 1 downstairs toilet, 1 internal ensuite bathroom. And what we're doing is we're going to add up these numbers to see what the mechanical extract is for them. So the kitchen, how many kitchens have we got? We've got 1. So we're going to add 13. How many utilities have we got? We've got 1. So we add on 8. How many bathrooms have we got? We've got 1 bathroom here and another ensuite bathroom here. So we have 2 bathrooms. How many sanitary accommodations without a bath or a shower have we got? We have got 1 downstairs toilet. We add on 6 for that. So here's the sum. We add 113, 1 8, 2 bathrooms, 2 8s, 1 6, and we get 43 litres per second. This is the amount of air that's required to pull out the moisture to ensure ventilation of these wet rooms. Now, recap. We did the general ventilation rate. We also did the mechanical extract for the wet rooms. The system is required to be 25% bigger than the calculated ventilation rate that we just calculated. So it needs to be, this is like an excess to make sure it's not right on the edge of it working. So we have a 25% buffer in order for this to work. So if you remember, we had the general ventilation rate was 39 litres per second, and we now need to add on that and 25%. So we basically have 39 multiplied by 1.25 gives us 49 litres per second. So let me stop the share for a moment. There's the thing that we first of all worked out. Then we worked out the extract from wet rooms, i.e. kitchens and utilities and anything that's generating heat in effect. Let me go back a couple of stages here. And that value was 43 litres per second. Switching over now again. So that was the extract from the wet rooms, 43 litres per second. We then have the general rate plus 25%. So it's 39 litres per second multiplied by 1.25, and that gave us 49 litres per second. That gives us that. Okay, back to the slides. I'm going to reshare the slides again, just giving you a recap. Send you a chat message. Shall I give a quick recap again before we start moving on to another example? If you give me a thumbs up, would you be interested in another recap? Yes, okay. So here's a recap again. We're going to be doing these a few times, so I wouldn't panic about it yet. And we're going to do it nice and slowly. So here's the general ventilation rate calculation. We had method 1 where we worked out 5 liters per second plus 4 liters per second per person. And then that's method 1. And method 2, then we had the area multiplied by 0.3. And we choose the greater of those two numbers when we work them out. So the greater of those two numbers was 39 liters per second. We then did a load of calculations for how many kitchens there are, how many bathrooms there are, how many toilets, and the number that we came out from that was 43 liters per second. Then said, we can't have it working right on the edge of it working. What we need is the general rate and a little bit of leeway. We add on 25%. And the way to do that is that we multiply the greater of the two numbers we worked out earlier, 39, and we multiply it by 1.25. And the answer is 49 liters per second. So I'm going to go back to the screen again. I'm going to share PowerPoint again. That's where we got to. And we worked out that the general rate multiplied by 1.25 was 49 liters per second. Now, that works out the two, okay? We now have two numbers. We have the extract from the wet rooms at 43, and we have the general one plus 25% is 49. The total capacity of the ventilation system required for this is the greater of those two numbers. And the greater of the two numbers is 49 is greater than 43. So we choose at that point which one is the greater of those two. And 49 liters a second is the total capacity of the ventilation system that is required for a 130 meter squared semi-detached house with those bedrooms. Now, we've got another example to do. So if you imagine a liter of milk and fill that, take out the milk, obviously, and then put air in there. So we need, in order to stop mold growth in a house of that size, we need 49 liters, 49 cartons of 1 liter milk every second going through the house in order that you do not get mold growth in your wet rooms. Now, I'm sure many of you are living in student accommodation where in the showers, go up into the shower, look up onto the ceiling, and you've got black mold growth on the ceiling. That's because of poor ventilation. It also occurs when you've got cold bridging, but in wet rooms, ventilation is very, very, very important. Okay, I'm going to stop. No, I'm not. I'm going to carry on. Now, we're not going to do this. We're not doing the calculations on this, but I'm just going to mention it, that extract should be from each wet room. The continuous extract ventilation rate at each extract point is meant to be for each room. We don't know the areas of these rooms, so you have to adjust it proportionally. So you're adjusting these rooms proportionally. So that is the continuous one on each room. I'm just mentioning it to you that this is another part of the calculation, but we're only going to work out now just the key number. You can see how it adds up to be 39 here. So we're going to do another example now. So what I want you to, oh God, I'm just changing the screen around, sorry. Okay, put that there. Bear with me a second while I just stretch the screen a bit. So this is example number 2 that we're going to work through. That we have, let me pause, hold on, manage participants. Sorry, apologies. Okay. This is example number 2. And now this is where you are going to require your pen and paper and calculator. And at the end of it, we're going to pause and see if we can come up with the right numbers. Okay. So this is for a similar type of calculation, but this time it is for a 80 meters squared, 2-bed apartment where you have 2 bedrooms, 1 bathroom with a toilet, and 1 living kitchen area. So it's exactly the same process of what we did a moment ago. And what would be really good if you've got a PC, I did email you the slides in advance in case you need to go back and check anything. So first part of the calculation is where we are opening the, we're working out the general ventilation rate. So we need to have 5 liters per second plus 4 liters per second per person. So we're assuming 2 people in the main bedroom and 2 people in the second bedroom. So, sorry. We therefore have 5 liters per second plus 4 liters per second by 4. So we have 21 liters per second. Let's go back. Have you got your pen and paper to work out that sum and keep it to one side? 2 people in the main bedroom and 2 people in the second bedroom. So we have 4 liters per second multiplied by the number of people 4, add on the 5, and we get 21 liters per second. Give me a second. Sorry. Calculate, so we then work out the calculated general ventilation rate based on the internal floor area of the building. So that is done by multiplying 0.3 by the area. And the area is 80 meters squared. So on another piece of the paper, work out 80 multiplied by 0.3. I'll give you a couple of seconds to work that out. And the answer is 80 by 0.3 is 24. So what we're now doing is we're choosing which of these two is the highest value, and the highest value of 21 and 24 is 24. So the general ventilation rate of the dwelling is the greater of the above. We have two numbers, 21 and 24, and the greater of those two numbers is 24 litres per second. That's part one of the calculation that we're working on. We then have this table again, where we have the amount of mechanical extract ventilation systems, where we have kitchens, utilities, bathrooms, overall sanitary ware. I actually practiced this lecture yesterday to my son, and he was saying, oh, is it 13 squared? I said, no, that 2 is the, it's a footnote to the bottom, and it's not 6 cubed either, so it's 13, it's just a footnote, well, super note. So we have, in this flat apartment, we have 2 bedrooms. We have 2 bedrooms, 1 bathroom with a toilet, and 1 kitchen living area. The sums for this are a lot easier. So what we have, 1 kitchen area, 13, 1 bathroom, 8. Add the 2 together, we get 21 litres per second. So we then compare the 2 numbers. We compare the 24 that we worked out. This is the greater of the first set of calculations. Then we work out the same calculation using the mechanical extract on the wet rooms, and it came out as 21. So the general ventilation rate is 20, is the higher of those 2 values, which is 24. But we can't have just it working at 24. What we need is it to be 25% over that to give us a little bit of leeway and a little bit of room. So we work out 24 multiplied by 1.25 gives us 30 litres per second. And 30 litres per second, what is the total capacity of the ventilation system required is the greater of all these numbers that we've worked out. This is the total capacity of the ventilation system, and it is 30 litres per second. Now, this is the same calculation for the for that apartment, that you're able to work out the bedrooms by what the room volume is. I don't know what the room volumes are, but this is a separate calculation in order to get the general supply rate for each individual room. Now, is this relevant? You've been taught that you need to understand the building regulations, and these regulations on ventilation are really, really important. We had to pause there for a second. I wasn't going to do that one. We're going to skip that one. We had to do some background ventilation calculations for some Galway City Council houses, their council houses in Galway, where we had to work out the areas of these rooms and then work out the extract ventilations of the spaces and what the size of the rooms needed to be. So you may be asked to perform and work out these calculations. My advice to you would be, however, to get somebody to supply and provide a mechanical heat and ventilation system. then get them to supply the calculations. And then you should do due diligence and check them and let them take the responsibility of compliance with the building regulations. Because these windows, these had background ventilators in them in order to provide ventilation. I've got no idea of how to measure. You could work out an area, but there's grills in them. It's very difficult to go in and measure sizes of grills and things. You're better off having a mechanical heat and ventilation system and let somebody else take the calculations off you for this. But what you are doing is the principle of these calculations so that you understand how much air is required in these spaces to prevent condensation and mold growth in buildings. Now, I'm going to stop the sharing of that. In a moment, what I'm going to ask you to do, and you're going to have an hour and a half, 2 hours to do it. I'll give you an hour to do it. I would like you to go through the calculations again, and I'm going to send you an email at the end of this lecture, and I'd like you to do it for your student accommodation where you're living now. And if you want to practice, you could do your own house as well. The calculations based on your own house and your student accommodation. So I'm going to stop the slideshow there. I'm going to unmute all of you and unmute all. And I'm going to type a message to everyone here. Is everyone clear what I'm asking you to do? Yes, excellent. Yes. Yes, perfect, good. If you are in any doubt, I'm accessible on email. I'm here all day today. So what I'd like you to do is to produce those calculations and then email them to me to my IT Sligo address. You can reply to one of the ones I've sent to you previously. Work out the calculations, do it really neatly, step by step by step, exactly like part F. Work out the calculations, email them to me, and at 3 o'clock, when we start the professional studies lecture, I might have a recap over them then at that point. So I'm going to sign off on this lecture for the time being. If you have any questions, email me, and then I'm going to see you again, not at 2 o'clock. It's going to be at 3 o'clock because there's a staff meeting on Teams at 2 o'clock. So I'm going to see you at 3 o'clock for the professional studies, and we'll have a recap on what we've done this morning, and then what we're going to do is start on in the afternoon. We're going to finish off what we started before we left on Friday about the BCMS stuff. So I'm going to say goodbye to you, and we'll see you at 3 o'clock, 3 p.m. on the second invite.